Okay, so welcome everybody to our session on general contributions to solid Earth geophysics. Apologies for the late start, we had some technical issues. Just a quick reminder before we start that if you have questions for any of our speakers, please type them into the chat and I will be able to read them out to the speakers after their presentations. So we're a few minutes behind, so without further ado, I'd like to introduce Kelvin Klatt from Natural Resources Canada, who's going to talk on Canada's National Quantum Strategy, a role for geophysics. Over to you.
Okay, so actually we're going to start with my co-author, Aimee Gunter, and Aimee, can you get the deck, share the deck? So yes, so it's going to be a joint presentation, myself from Natural Resources Canada and Aimee from the NRC's Quantum Challenge program. So I'll over to Aimee.
Good morning, everyone. All right, so before we get, quantum definitely brings fear to many people when I speak to it, but I'll start today with a quick definition of that. You know, this call today is enabled by quantum technology. This is a fact here, but that's not exactly what we're talking about today. So it's true, you know, today's devices like the transistor and the laser, one of my personal favorites here, definitely require the theories of quantum mechanics to be able to enable them to work here. But today's talk here is really discussing quantum 2.0, which is now advanced to the stage where we're able to manipulate, create, and contain superposition and entanglement, these unique properties of quantum mechanics, far enough along that we actually can start applying them towards things. Like there's whole fields of quantum sensing, quantum computing, quantum communications. So we're far enough along that we're not just in basic research stage. And relevant for this crowd, as Kelvin will mention a bit later, like there are some things that be starting to be used now in this field. So what today we're talking here is how is Canada's stake in quantum relating to the National Quantum Strategy, which was announced last year. So budget 2021 and announced 360 million over 7 years with, to really amplify and develop Canada's strength in quantum research. It's not well known in Canada that we actually are doing pretty well, all things considered, in quantum. Like considering we are just small players, in the grand scheme of thing, Canada does have some strong leadership in this area. So this national quantum strategy is an attempt to, actually try to build off of that. So in February of this year, the ISED, who's the one who is creating this, writing this national quantum strategy, which is not yet out, launched released a What We Heard report, which explained a lot of the consultation results of previous years. So those were research, commercialization, and talent were the key areas that the strategy would likely need to address, with cross-cutting themes such as security, like research security in this hot button topic here, international cooperation, and intellectual property. So for the remainder of my half of this talk, I want to quickly highlight some of the areas and how, of course, for this audience, how this can be engaging with it, and what programs are around that this strategy will likely take part of. So Canadian ecosystem in general, like I know from the academics here, this is something you navigate every day. On the research front, on the quantum bit, of course, there's an NSERC discovery grants, how's your equipment doing these days, you CFI and whatnot. So in the quantum programming landscape, we have the basic research front there. On the talent front, different research chairs, NSERC Create, MyTax is definitely a player around here. And then on the innovation part there, more the commercialization pieces, there's a variety of programs that kind of push up the technology readiness scale, generally speaking here. I'll be talking about my program here a bit later. But what has been announced to date on this strategy, right? We're in year 1 already of this national quantum strategy. So what has been announced from publicly that I've been able to find here is NSERC. So for the NSERC folks in the crowd, they have a quantum themed alliance stuff, and MyTax got money from the budget 2021 as well. And I will say a few words about this. So from the NSERC website recently, 37.9 million out of 360 million is going towards on the research front here. Through their alliance grants and create grants. I would like to highlight right now that for this audience, like of true, end user experts here, quantum physicists, may be good at, keeping the atoms isolated from the environment, but, they don't really understand best how to use it. So this is, I think, would be the, being a part of a team type of alliance grant would be perhaps one of the better ways to do it. I'd recommend. Other programs is my program. I'm part of the NRC Internet of Things Quantum Sensors Challenge program. So at the National Research Council, we have NRC researcher plus academic or startup together on these collaborative projects, and our program is consisting a bunch of collaborative projects together here in the sensing domain of all the different types of quantum sensing system. And so we did receive some budget money just to kickstart it, because out the door there, and with our colleagues from defense as well, our program is actually one of the largest challenge programs within the NRC at about 46 million over the 7 years here. And then another program of interest, maybe more broadly to the crew, is the Innovative Solutions Canada. So this of course is on the higher TRL side, but this is just the government putting out challenges. Hey, is anyone able to solve some of these things? They do also have a lower TRL version there that's more on the a little easier to access there, but this is definitely a program to be watching in the future. And this, I'll pass it to Calvin.
Okay, thank you. So we're racing through this to, so the quantum technologies that IMA's mentioned, and remember, this is the kind of the new quantum that enables these new capabilities. So they're kind of, I break it down into the three things: quantum computing, communications, and the quantum sensing or metrology side. And interesting for us, I think, for the geophysics community, is going to be the quantum sensing metrology, and those systems are gravimeters, magnetometers. There are radiation sensors, clocks, and laser systems. What we found within our discussions at Natural Resources Canada among the geoscience group is that gravimeters and magnetometers are probably of most interest right now. So I may next. So the gravimeters are now commercially available, and I can announce today that Natural Resources Canada is purchasing a quantum gravimeter. It's quite a large amount of money, and it took me several years to get that funding, but it has been approved, that purchase. So we will have a quantum gravimeter. They are comparable or better than the best ones that can be field deployed, the absolute gravimeters. They are absolute in that they don't appear to drift. They can be deployed like on a volcano for months at a time and continuously collect data. So they have very different characteristics. You can imagine at one time Canadians actually measured gravity with pendulums, and then eventually people that was a very difficult technology to use, and they moved to spring gravimeters. So basically the use of an instrument really will require a lot of practice, and that's, I think, that part of the quantum strategy should be that there's this other element of us learning how to use new instruments, learning to maximize the benefits of that. The other area that we've looked at is within Natural Resources Canada are magnetometers, and I'm definitely not an expert in this, but a couple of different groups have talked about how that could be a bit of a game changer for their work, and I'll give some examples next. So next slide, please. But I think the key message is really that these instruments are going to be pushing the boundaries of what we can measure in the geosciences, and we may see there's going to be either from increased accuracy of the instruments or increased sensitivity in time, or lack ability to measure consistently over months at a time with high repeats. All of those kind of changes are going to give us new information that we've never observed, and I think NRCan is purchasing a gravimeter, this year, but I think we're at the very beginning of the whole quantum world. The next generation, there'll be a generation, coming later, where they're using different aspects of the quantum 2.0 technology to drive this even better. And we know, like satellites, Grace follow on, they're talking about using quantum sensors on this. So there's going to be kind of a bit of a revolution occurring, and we'll have to see how that bears out in the future. Next slide, please. So just a couple examples. I know we're coming right up to our time here, but my colleague Vicky Cherhart in NRCan has talked about using quantum magnetometers or magnetic radiometry to look at ore systems, and part of it is not so much there's the sensitivity, but also there's higher resolution in other ways that then make it a better technology. Next one, please. So with gravimetry, we know that often gravimetry is a complementary to INSAR or LiDAR or other techniques. So, and also looking at mass changes and so glaciers, looking at carbon capture and storage. And here, an example here is the glaciers in Alberta. That's just from CBC News last month. And maybe episodic tremor and slip events. You can basically monitor an entire event without drift problems or having to stand beside the instrument 24/7, basically. So on to the next one. So I mentioned NRCan is buying a quantum gravimeter, and we want to use that to provide a bit of a feedback towards the whole quantum strategy. So we have an arrangement with Brindley Barrett of UNB, who is interested in building gravimeters, like a better version of the gravimeters, and he would like to use this to, he did some of his studies were in France, and he knows the company, and he's interested in borrowing it to characterize his own laboratory, but also to look at it in terms of how he might do a better job in a Canadian-made Canadian instrument. So I think the point of this all is that I guess the message is Canada, there is a new technologies coming. Canada is quite invested in that. We have world-leading experts in many areas there. We're trying to, I guess collectively figure out a way for the geoscience community, which is definitely a well-documented user of that technology, to maximize its benefit from it. And so we have IMA and others who can maybe help us understand how the funding could be arranged or obtained to work together with the others. So I think next slide, I think we're done. And I think it's 10:40, so I'll pass it over to Fiona.
Okay, thank you very much. In the interest of times, because we started late, I think we'll have to move on rather than taking a oral discussion question session. However, if you want to ask questions to Aimee or to Calvin, and I see there's already one come in, please feel free to type them into the chat. And Calvin and Aimee, I'd encourage you, if you have a chance, to type a response in, and we'll be able to see those. So moving on to our next presentation, it's by Omid Bakapou-Mojave at University of Quebec in Montreal, and he's going to talk about seismic structure of the lithosphere in Eastern Canada using earthquake and ambient noise seismology. So Omid, go ahead, share your screen, and it's all yours.
Thank you very much, Fiona. Can you hear me clearly?
Yep.
Okay, right. I'm going to share my screen now. So do you see it now? All right. All right, thank you very much. I'll be discussing and summarizing the results of 2 chapters of my PhD thesis that was about the seismic structure of the crust and mantle lithosphere across Eastern Canada and the Northeastern USA. So the results you're about to see are recently published, and you can see the titles of these publications at the bottom of this slide. So a little bit about the tectonic history of the region. Tectonic history of North America is very complex. At the center of the continent, there are multiple long-lived Archean cratons that are welded together by Proterozoic belts. And these domains together were once called Laurentia. Laurentia is now surrounded by some Phanerozoic mountain belts of various age. I have marked the study area located in the eastern North America by the red ellipse in this the left map. Our study area includes mainly the Phanerozoic northern Appalachians, as well as eastern portions of the Proterozoic Grenville origin, and the largest craton of our planet, the Archean superior craton. The current shape of our study area was complete after a series of collisional and accretionary episodes related to terrains either originally belonging to Laurentia or another ancient supercontinent at the time named Gondwana. The main objective of these studies were to obtain highest resolution tomography models covering crustal and mantle lithospheric depths. And by using these models to discuss tectonic implications. Now in seismology, there's no single type of wave or method that could do it all for us. So we need to combine methods and data sets in order to take the most detailed look at the crust and the mantle. So I did. For the crustal depths, the method used is called ambient noise tomography with the acronym ANT in this slide. In this method, we cross-correlate the process noise data for pairs of stations that will give us a special sort of surface wave traveling between the station pairs that seismologists call empirical Green's functions. On the other hand, teleseismic earthquakes could also be used to extract surface waves, and the method I use for this purpose is named two-plane wave tomography that takes into account some undesirable effects in the waveform, such as multipathing and scattering. In this method, the incoming wave field is assumed to be as a result of interference between two plane waves, and by tracking this interference across the inversion grid, we could ultimately obtain velocity structure at mantle lithospheric depths. Now from this slide onward, you will see I'm comparing the results and processes related to ambient noise tomography method on the left with the ones from the two-plane wave tomography, which is an earthquake-based method on the right. So this is a slide, for example, is all about comparing the data sets and comparing the two. The study area, in the case of ambient noise tomography study, is slightly larger, covering some southeasternmost parts of Superior Creighton, as well as more areas of the Grenville province, whereas the study area in the two-plane wave tomography is mainly covering the northern Appalachians. In both methods, I used vertical components data recorded between 2013 and 2015 to analyze Rayleigh waves, but of course, the types of data is very different. In ambient noise tomography, we actually have to remove earthquake signals from data, whereas in the case of two-plane wave tomography, we're dealing only with the earthquake data. Now, there are some example process data for the two methods. These are, for example, on the left, you're seeing example process data for the ambient noise tomography, and on the right for two-plane wave tomography method. Some of these processing steps are actually very similar. For example, resampling the time series for coherency and reducing the storage size, and removing instrument response from the time series to make them comparable. But some of the processing steps are also unique to these methods. For example, in the case of ambient noise tomography, we need to ultimately cross-correlate the data between the pairs of stations. So we apply some pre-processing that is required before the cross-correlation. So I did, for example, apply 1-bit normalization to remove the earthquake signals from the data. And I also applied the spectral whitening to flatten the noise correlation functions in the frequency domain. For the case of two-plane wave tomography, we first isolate the teleseismic surface waves, and then we apply bandpass filters to different corner frequencies. What is common between the two is that we study the dispersion characteristics of the emerging surface waves to obtain variations of phase velocities as a function of period or frequencies. And these variations are sensitive to Earth structure, which is exactly what we're looking for in the tomography study. So I've divided the discussion of the tomography results into 3 subsections, and the first one is phase velocity maps. So phase velocity maps are the main outputs of a surface wave tomography inversion. It's important to know that they show integrated information about the structures at certain depth range, depending on the period, and not the velocity of a particular layer. To get shear velocity at different layers, we need to actually take another step further and invert the phase velocity maps. So in these maps, periods are shown as the first number on the bottom right of the maps, and the other numbers are the average phase velocities at the given periods, because the phase velocity variations in these maps are given in terms of perturbation from the average. On the left, you're seeing the phase velocity maps related to ambient noise tomography study, mainly covering cross-salt depths. It's clear that in North Appalachians, it's largely dominated by slow anomalies, whereas in the Grenville province, velocities are relatively faster. So the magenta bars, for example, on the phase velocity maps in the left maps, they are showing azimuthal anisotropy results, which is the only done for the ambient noise tomography study. And the fact that they are parallel to the orogenic strike along northeast southwest, it suggests that the orogenic evolution is mainly preserved. There are some localized anisotropy anomalies across the Bay of Fundy and crossing the Appalachian structural front, which could be due to resetting of anisotropic fabric or fossil anisotropy. On the other hand, side of this slide, on the right, you're seeing the results for two-plane wave tomography inversion, covering depths from lower cross to sublithospheric depth. So we have some depth overlap over here. These maps are cropped using a particular confidence interval contour information that is extracted from a standard error map, which is a product of the inversion results. And looking at these maps, it's clear that seismic structure of the lithosphere across the study area is very complex and variable. But in order to give a better interpretation, we need to actually invert phase velocity maps. Now, before doing that, it's a standard practice to assess the resolution of the models using a structural and checkable resolution tests. These are some example resolution tests for the two methods, and there are many more tests done in the published papers. In these tests, an input synthetic model is inverted at different periods, considering the exact same path coverage and regularization setting for the final inversions. The input models are shown at the very top of these figures. In the left, the synthetic structure is designed to mimic the observed main features of the phase velocity maps. And in the right, the checkerboard pattern has a cell size of about 160 kilometers. These tests suggest that our tomography models are reliable and the input features are generally well recovered. Now it's time to invert the phase velocity maps for shear wave velocity model. Now, similar to previous slide, you're seeing shear wave velocity models for ambient noise tomography study on the left and the results for two-plane wave tomography on the right. Both of these two models are pseudo 3D shear wave velocity models in the sense that they are made after combining 1D inversion results at single points. Now, it's a standard practice that cross-salt studies show absolute velocity variations, whereas studies of covering mantle depths show their maps in terms of perturbation from the average, from the reference model, in this case, AK135. A complexity of seismic structure is again clearly visible in both shear velocity models. Now, in order to interpret thickness of the sedimentary layers or crust or even lithosphere, we have to use some seismic proxies. And for example, features with velocities less than 3.4 kilometers are interpreted as the first sedimentary layer. And following this choice, we can interpret that the sedimentary basin across the Gulf of St. Lawrence could be as thick as 10 kilometers, or across, for example, St. Lawrence platform, it could be 6 kilometers. Across the Bay of Fundy could be 4 kilometers. I also use the seismic proxy to obtain MOHO depth maps. And you're seeing the results at the bottom right figure of the left panel over here. One interesting observation here is that we are seeing a very sharp contrast within the northern Appalachians that is like a MOHO step feature in our model. And I did shown that with this dashed black line. This feature could be marking the boundary between the pre-Gondwanan and pre-Laurentian units at depth. I'd like to also note some interesting features of our two-plane wave tomography model. For example, it's clear that the velocity across the eastern North Grenville and the pre-Laurentian domains of the northern Appalachians are generally higher than that observed for the pre-Gondwanan domains. And another very interesting model feature is that we have a very high velocity zone across the New Brunswick. And if we consider a contour of 1.5% perturbation above the reference model as a proxy to locate the LAB depths, we can infer that the LAB depths varies in 70 to 120 kilometer depths. And the lithosphere is locating beneath the New Brunswick is the thickest 120 kilometer depths. This also could tell us there is no simple relation between the accretion of the age of the terrains and their lithospheric thickness. Now, just a few notes about the tectonic implications. So in our cross-cell model, we can see, for example, these Moho step features in the cross sections. We can see the location of the cross sections in these maps. For example, these Moho step features can be seen over here and over there. Another interesting model feature in our model is that seismic signatures across the northern Appalachians are highly valuable, whereas in the pre-Laurentian domains is less valuable. For example, the velocities varies less, and also the crustal thickness is more simple. Now, comparing to the northern Appalachians, the lower crust across the Grenville is much thicker and faster. As you can see, you see more blue on the left side of these cross sections, which could be due to partially ecologized lower crust or existence of Archean partectonous lower crust beneath these regions. Just a small note about tectonic implications of the mantle lithospheric model. For discussing these, I would like to draw your attention in this region, this very thick lithospheric region beneath the New Brunswick area. And this could be interpreted as 120 kilometer depth lithosphere within Ganderia. And it's very unusual because Ganderia usually is believed to have thinner lithosphere across the northeastern USA and across the Newfoundland, and it was very interesting. What can explain this observation is the stacked flat slab subduction. There are some evidence for occurrence of flat slab, including a fast convergence rate between the arriving Avalonia domains and the composite Laurentia, and it's from the palomagnetic studies. And another evidence is a cratonic-like composite Laurentia at the time of accretion, and also a bimodal age of volcanic rocks due to occurrence of 2 episodes of magmatism after a flat subduction. After initiation of the flat subduction, we have a period of magmatism, and then when the slab breaks off, we have another period of magmatism. So it's another evidence for the flat subduction. We also have some geochemical evidence for flat subduction in this region, particularly some high isotopic ratios for this region, which is usually seen in a flat slab setting. Finally, I'd like to speculate that perhaps the anisotropy reworking across the Bay of Fundy that I showed you in the phase velocity maps could be due to occurrence of the flat slab subduction. I don't have a summary or conclusion slide, but I would like to draw your attention to 2 of my recent projects on GitHub that you can contribute and download freely and use them for data acquisition and data processing of earthquake or ambient noise seismology studies. Thank you very much.
Thank you very much, Omid. I'm afraid we don't have time for questions and answers live, but again, please feel free to type your questions into the chat, and Omid, if you can keep an eye on the chat, then and type your answers in. And if you can stop your screen share, please.
Sure.
Thank you very much.
You.
So our next presentation is the first of our student presentations. It's by Mirtod Samali from York University, investigating how the accelerometer measurements of the Grace C satellite are affected by geomagnetic disturbances. So please feel to share your screen and take it away.
Thank you. Okay, give me 1 second. Can you see my screen?
Yep.
Okay, perfect. So good morning, everyone. My name is Mirtod Samali, and I will present my work entitled Investigating How the Accelerometer Measurements of Grace C Satellite Are Affected by Geomagnetic Disturbances. So my work is focused on Grace follow-on mission, and this mission is similar to Grace and consists of 2 satellites, Grace C and Grace D, that monitor the gravity field variations of the Earth, with one following the other at about a distance of 220 kilometers apart. They orbit the Earth, at an altitude of around 490 kilometers with an orbital period of 94 minutes. The main goal of this mission is to monitor the gravity field variations. In order to do that, we need two important instruments, the GPS and the accelerometer. By determining the gravity field variations, we can observe how the water and mass redistributes around the globe, and therefore we can monitor the climate change. For an accurate determination of the gravity field, though, it is crucial to measure the non-gravitational accelerations from the accelerometer with a great precision in order to subtract them from the total accelerations of GPS, so we can derive the purely gravitational accelerations for the determination of the gravity field. So the non-gravitational accelerations are the accelerations caused by the non-gravitational forces. Their investigation has been a very demanding task and topic of discussion among the researchers, since they provide us with an insight about satellites' environment. The most dominant forces acting on the satellite are the drag, the solar radiation pressure or SRP, and the Earth radiation pressure or ERP. The drag, which is the resistance of the Earth's atmosphere, always points on the opposite direction of the satellites, and it affects primarily the along track direction, which in our case of Grace Foe is the x-axis of the accelerometer. It is crucial to know the drag force for the orbit determination, since it's the main cause for the decrease of the satellite's lifetime. The most notable non-gravitational force acting on Grace Foe is the solar radiation pressure or SRP. It affects the three axes of the accelerometer, and it changes with respect to the satellite's position towards the sun and the solar cycle. Part of the SRP are the penumbra transitions, where it appears as jumps when the satellites enter and exit the Earth's shadow. The last non-gravitational acceleration is the Earth radiation pressure, which represents the Earth's reflectivity. It changes varies based on the Earth's surface, and it affects primarily the radial direction, which is the z-axis of the accelerometer. I would like to point out here that the accelerometers measure the sum of the non-gravitational accelerations, and therefore the modeling of its components is not only very important, but also very challenging. Numerous physical models have been presented throughout the years, which are based on the satellite's characteristic and the physical properties, and these models have been used for calibration purposes, since the accelerometers cannot be calibrated on the ground. So for a proper analysis of the residual series, my work is divided into three parts. So the first part is to create an alternative data set compared to the original one, which is called ACW1B. Our data set is called ACW1B and contains the variances of its filtered value. This data set will be used as an input for the modeling of the drag and the solar radiation pressure directly from the measurements of Grace C. The residual series after the modeling will be investigated using signal decomposition. To derive the ACW1B data set, as we can see here, I'm so sorry about that. As we can see here, to derive the ACW1B dataset, which is going to be our data set, we create a weighted 1A data set, which is 10 Hertz, and we took the variances. So these variances are introduced to the Gaussian filter of 35 millihertz, along with a fully populated covariance matrix. So therefore, after the variance propagation, our filtered values, along with the variances, have been calculated. So in this graph, as we can see here, the radial direction or the z-axis is displayed, and we can see that from our data set, even if our spikes are larger, we have variances, so therefore they do not contribute to our solution. The importance of a weighted data set is, especially in our analysis, is that our analysis is based in the frequency domain. So therefore, any spikes that contains high variances, they do not contribute to our solution. And this is very important, especially for graceful O1 measurements, where the Y and the Z axis present spurious spikes. So after the error propagation, all the models and the residual series are derived with the weights. This weighted data set was used as an input to model the drag and the SRP directly from the measurements of Grace C, which is something that has never been done before. The importance of this model lays down to the fact that the physical models of the drag present large inconsistencies with the measurements, and therefore, when they're used for calibration purposes, they might introduce some errors. In this graph, our dataset is displayed here for 3 consecutive orbits, and we can see that each orbit consists of the saddle part here, the penumbra transition, and the sun part of the orbit. The orbital period is about 94 minutes. So to model the drag, we select the saddle parts of the orbit and the midpoint of the sun part of the orbit, because this is based on the principle that in these points, the SRP is equal to 0, and the drag is the only dominant force acting on the satellite. So using the least square spectrum analysis, we model the drag using 2 resonant frequencies very close to the orbital period and the semi-period, and these agree with the theoretical drag models as well. We subtract from the data set the drag model, and we derive the RP, or the radiation pressure, which in the x-axis contains the solar radiation pressure, thermal and earth radiation pressure, and shorter drag variations. After modeling using the least square spectrum analysis, we model the RP using 4 frequencies very close to the orbital period and its 3 harmonics, as we can see here. Again, these frequencies agree with the physical models of SRP. By subtracting the 2 models from our data set, we derive a residual series, a weighted residual series that contains some structure signals that we will investigate further. In this graph, 1 year of measurements of accelerometer measurements from August 2018 to 2019 are displayed in blue. I'm so sorry. We can see here the accelerometer measurements are strongly correlated with the beta angle variations, which is the angle between the orbital plane and the sun. So we can see in these 3 cases where the beta angle is larger than 70 or smaller than -70 degrees, the satellite is in a full sun orbit, and that means that we don't have any penumbra transitions, and therefore the amplitude of the accelerometer is smaller. Also, in these 3 cases, the SRP is less intense. We can see in red, we depict the sum of our 2 models, and in green, we depict the residual series after the subtraction of the 2. The mean of the residual series is about 1.5 nanometer per second squared, but we can see some higher values when we have a KP index larger than 5, which is an index that indicates the appearance of geomagnetic storm. The analysis of the residuals has been implemented using wavelets of 13 levels. From the power spectral densities of the residual series, we've shown that after 9 millihertz, which is about 110 seconds, our signal contains just noise, and therefore we low pass filter it. From the signal decomposition, it's extracted that the residual series contained a very low frequency signal in the band of 0.1 to 0.5 millihertz, which corresponds to 33 to 95 minutes. And these signals can be attributed to the ERP, probably based on the world map, that we can see some structures above the continents, but this needs to be investigated further. The next band is from 0.5 to 4 millihertz and contains the drag variations due to atmospheric changes that can last up to 4 minutes. We can see some sort of variations, and these variations are in agreement with the variations in the saddle part of the orbit, where we know that the drag is the only force acting on the satellite. The last band that we're interested is from 4 to 8 millihertz and contains disturbances connected only with a pulse crossing that lasts from 2 to 4 minutes. In our analysis, we're going to ignore any signal that is below 0.5 nanometer per second squared. We can see here on the left that during quiet days, we can see strong disturbances only in the descending orbit when the satellite crosses the 45 degrees latitude south. Also, we can see some disturbances in the North Pole not only in the ascending, but also in the descending. But this behavior changes a little bit when we have a storm. When we have, for example, geomagnetic storm of Kp larger than 5, we can see that we still have this structure signal in the descending orbit of the South Pole, but also we can see that the North Pole is way much more affected, and we have higher disturbances, especially in the main phase of the geomagnetic storm, which is in about 10 UTC hours, and the disturbances can reach up to 10 nanometer per second squared. So after the signal decomposition, we attribute the sorter variations that we found to the drag model, and the final SRP is displayed in green, and the drag model displayed in yellow are shown here. To summarize, with a weighted data set of 1A and 1B is provided for GRACE C, and the first weighted drag and SRP data-driven model has been derived for GRACE C measurements. Disturbance is only connected to field-aligned currents or to pulse crossing or to the appearance of geomagnetic storms can be shown in the measurements, especially in the frequency band from 4 to 8 millihertz that corresponds to 2 to 4 minutes. My next step is going to be to derive the drag and the SRP models for a year for SWAM mission as well, for comparison purposes, to attribute the low frequency signals to the Earth radiation pressure or to thermal radiation, and lastly, to investigate the residual series of the Y and the Z axis using a more sophisticated filter method due to the fact that these two axes contain spurious spikes that needs to be filtered a little bit more further. Thank you so much for your time. I will be more than happy to answer any questions.
Thank you very much, Myrtle. Again, in the interests of staying on time in the session, we'll have to move on. But again, please feel free to type your questions into the chat box, and Myrtle, if you can keep an eye on that and
sure,
look out for any queries. So the next couple of talks are actually short talks, which are designed to advertise two posters that we received for this session. So 2 3-minute talks. And the first one will be given by Nato Georgiashvili from Ilia State University in Georgia about seismic network deployment and updated ground motion prediction equations for Georgia Caucasus. Thank you.
So I will just share my screen. So good morning, everybody. When in my country is evening here. I'm going to talk about seismic network development and updated ground motion prediction equations for Georgia Caucasus. So as you might know, Georgia is situated within the Caucasus region, so it's very with moderate seismicity. So it's in Alpine Himalayan collision belt. So recently our seismic network have been developing very quickly. So since 2003, so digital seismic network has been developing. So I have chosen 2 types of data sets for this study. So one of them was strong motion data set, which was operating in since 1990 to 1996. And broadband type network, which was operating, as I said, since 2003 up to now. So I mix this data set. So here you can see distributions of the data. Here in the red color triangles, you can see a broadband type seismic network, and by blue triangles, you can see strong motion data network. So then I have processed the data and developed GMP's ground motion prediction equations for my country. So it was actually the first attempt to do the little bit sophisticated models because until now we did not have enough data sets to process and obtain GMPs. So here you see a functional form which I used for the model. Here, this is the ground motion intensity part. So this part is related to magnitude. This part is F2 related to distance. F3 it's related to fault mechanism types, and F4 is related to soil, local soil conditions. So I have used European classification for site class. So mainly 3 types of site class we had used for seismic network. And then I could not input and poster coefficients which I obtained by this model, but because it was too long and it's difficult to fit in the poster, but I have included different models which I obtained for peak ground acceleration and spectral acceleration starting from 0.01 to 10 second period. So in this figure, you can see GMPs for peak ground acceleration for different magnitudes, for magnitude 5, 6, and 7, horizontal and vertical components. Here in this figure, you can see spectral accelerations, the same for different magnitudes 5, 6, and 7, and the thrust fault type for soil class A. Here you can see spectral acceleration for magnitude 6 and thrust fault type, different soil class A, B, and C class, and you can see clearly influence of soil classification on the GMPs here for spectral acceleration. And here you can see on this figure spectral acceleration for different fault types.
My apologies, but it is a 3-minute poster presentation slot, so I'm afraid I'll have to ask you to summarize.
Yes, and finally, at the end, I have obtained seismic hazard maps. I used classical studies for probabilistic seismic hazard assessment. So here you can see seismic hazard maps for 50 years exposure time, 1% probability for PGA, 2% probability, 5 and 10% probability. This is the final end of my study, and these maps were obtained using the new GMPs obtained also in this study. So this was our result. Thank you.
Thank you very much. And just a reminder, the posters are available in the poster gallery. So I would encourage all participants to go and take a look and see the work in its full detail. We have a second 3-minute poster slot right now by Yashangelia, also from Ilia State University, on intrinsic and scattering attenuation in the lithosphere of the Rahala region in Georgia. So you have a 3-minute presentation. Are you there?
Yeah,
Hello.
hello.
Can you share your screen?
Yes,
Great, and you have
Welcome.
3 minutes.
okay. The Racha region is located in the western Greater Caucasus. The main goal of the study is to obtain the attenuation properties of the lithosphere beneath the Racha area using the seismic Coda waves. In particular, we have estimated Coda wave attenuation as direct wave attenuation and the relative amounts of intrinsic and scattering attenuation. The attenuation property of the medium is characterized by the quality factor Coda Q, which is inversely proportional to the attenuation. The now results now. The obtained values quality factors, such factors are strong function in the frequency range of 10524 Hz and follow such power law, where Q0 is the quality factor at 1 Hz and N is the frequency parameter. Both these parameters are a measure of heterogeneity and seismicity of the region. In general, Q0 is low and N is higher in seismically active regions than for tectonically stable regions. The obtained quality factors increase both with respect, now this figure, both with respect to lapse time and frequency. The increase of Coda Q with lapse time can be explained by the change of attenuation with the depth, because wave arriving later in the seismogram may be scattering from deeper parts of the crust than energy arriving earlier. Our results show that this figure 8, that Coda Q is close to intrinsic Q, but both of them are smaller than scattering Q. So in the crust of the Racha area, intrinsic attenuation plays a dominant role than scattering attenuation in frequency range of 1 to 32 Hz. Comparison of our results with other tectonic and seismically active regions of the Earth show that the Racha region is characterized by low Q values and they are comparable with other seismically active and heterogeneous regions. High values of attenuation in Racha region can be explained by the geological age of faulting. Relatively late faulting is more distributed and inhomogeneous, the Greater Caucasus, where the study region is located, belongs to the relative young tectonic structure where the deformation are concentrated. Accordingly, Q values in such regions are smaller than those regions where the folding age is older. According to the recent GPS data, the Greater Caucasus is tectonically active with complete deformation. The observed high attenuation can be also be caused by the high heat flow under the Racha region and the low velocity zone which exists in the upper crust of the study area. And here it is conclusion. Thank you so much.
Thank you very much. And again, I'd like to encourage all participants to go and look at the posters in the poster gallery.
Okay, thank you.
Okay, so our next presentation is our second student presentation of the day. And it's going to be by Tianqi Liu from the University of Toronto, talking about shear velocity and anisotropic model of the Alaskan lithosphere obtained by full waveform joint inversion of ambient noise and local earthquake data. Yashengelia, could you finish your screen share, please?
Okay, thank you.
Thank you for your introduction, Fiona. Can you hear me all right?
We can hear you just fine, so you can share your screen now.
Okay. share. Oh, by the way, my presentation is also a poster.
Okay.
Yeah.
So
Yeah. So it's also a poster. Yeah, I have prepared a few slides, but you're welcome to check out my poster for more.
Okay, because the timing that was given to me in the session gave you a full length talk, so I wasn't aware that it was a poster. So
oh, I thought it's a break, or yeah, I'll just share my screen.
Sure, thank
Can
you.
you see it now?
Yes, we can see just fine.
Yeah, so I'm gonna talk a little bit about our project on using seismic tomography to study the Alaskan lithosphere. It's a collaboration between our group and various collaborators. So the aim of this study is to image the shear velocity and anisotropy for the entire Alaskan lithosphere using the newly available US array data. So the data that we use is ambient noise. Basically, we fetch continuous time series data, seismic data for almost 80 months, and process the data according to the standard procedure to extract the three-component empirical Green's function between station pairs. We filter the data into 3-period bands, and we measure the frequency-dependent travel time misfit between synthetic and data, and invert that for the shear velocity and anisotropy model using the adjoint tomography method. We start from a very crude initial model, and we iteratively update the model, as you can see in the animation, and trying to reduce the misfit at the same time. So the current tomographic models is displayed here. I won't go into the details, but I will just say the model includes various features, including, for example, thin and thickened crust, magmatic activities, slab features, and the mantle wedge on top, and also anisotropic features that reflect past and present deformation patterns. And in order to enhance the deep structures, the resolution for the deep structures, in the future, we are planning to include earthquake data, local earthquake data for inversion. But as you can see in Alaska, the distribution of local earthquakes are highly clustered, which is not good for seismic inversion. And in order to tackle that, we are going to use the so-called double difference measurement, which is proven to be effective to mitigate the effect of uneven earthquake distribution and enhance the lateral resolution. Yeah, I think that's it for the short introduction. And again, feel free to check out my poster and contact me if you have any question on that. Yeah.
Okay, thank you very much. And my apologies for misunderstanding the information on the session timetable, which in fact gives us about 8 minutes now between now and the next talk. I suggest that we keep to that timetable in case people are wanting to come in and join us. So we have a few minutes. Does anybody have any questions for any of the previous speakers or any points of discussion that they'd like to bring in? Okay, we have a question to Mirto. So from Jianyang Huang, who says, interesting presentation. Do you expect that your investigation will improve current GRACE products?
So we expect, unfortunately, because we don't have the software to derive the gravitational field of the Earth using the accelerometers, the weighted accelerometer data set. we are not able to have a result of how this will affect the gravity field. But for sure, it can be used towards with a physical model for the calibration purposes of the accelerometer in order to correct probably some errors that have been introduced in the calibration purposes due to larger residuals. And also because the graceful one, especially the two axes, the Y and the Z, present so many spikes and are very noisy, we propose the introduction of the weights in the solution, so we can reduce the noise from the Y and the Z axis.
Thank you very much. Are there any other questions? Are there any other questions for any of our speakers that we've had so far?
I'll go ahead, Fiona, if that's okay.
With the talk?
No, no,
Sorry.
I didn't mean to. Sorry,
Okay.
didn't mean to preempt that. I was going to ask. I see Calvin's still around.
Please go
Perhaps
ahead.
either to Calvin. Hey, good to see you again, Calvin. It's been a lot of years. I'm just curious to know, for those of us that want to kind of stay, in tune with the initiatives that you're working on with these exciting new quantum-based instruments, if there's a good website or something that you might be able to provide us with, or some other avenue.
Yeah, that's a good question. I wonder, maybe I can reach out to IMA and find out what they have, because I guess IMA is actually a quantum physicist and I am not. But yeah, I've kind of sort of done my research by Googling a lot of things, but I've had the benefit of working within NRCan, and I've probably spoke to at least a dozen scientists about quantum instruments and like trying to generate some enthusiasm. And I obviously also wanted to generate enthusiasm to buy an instrument, which I managed to acquire the money for. So anyway, I'll look into that, but I don't really have anything. But maybe you can reach out to me maybe later, and I'll see. I think one thing of interest is that we will acquire a quantum gravimeter. I think the plan is to deploy it in British Columbia and Alberta, kind of the glaciers and episodic tremor and slip events. We'll also be looking at in other places. So, I think we'll have to characterize that instrument and compare it to the other instruments we have. And so that'll be a process. But if people are interested in looking at it and working with us with it, that's something you should probably contact me and let me know about that.
Great, thank you.
Thanks a lot. And we also have another question for Calvin in the chat. How much do we know about industrious and private involvement on quantum technologies in Canada?
Yeah, there actually are a number of companies in Canada that are developing instruments. I guess there's I think it's SB Quantum in New Brunswick, Sherbrooke, Quebec, and there's others. So I'm not sure. Actually, IMA's group at the NRC are kind of reaching out to different groups in Canada. The instruments are generally not very mature, right? So there's not a big market. The Muquan's gravimeter, on their website, they say this is the only instrument available for sales. So, and I think that actually gravimeters are more mature than the others. So it's very early days, but there are Canadian companies. I have reached out to a airborne geophysics company, asking them about using quantum gravimeters, and they're kind of hedging their bets a little bit because they know that they're too expensive really to deploy extensively. So that so I guess there's the two sides. One is the companies developing instruments, but then there's this whole idea of using them. And I think that's still very early days. But the company I spoke to, they're aware of them, and they were reading some of the literature that came out of actually from some Rennie Forsberg published paper on these instruments. So, and there have been shipborne usage. So, it's still, I think, too early days for a lot of application but there's certainly the quantum strategy is trying to fund businesses to build and sell instruments.
Thanks a lot. I'd like to jump in with a very quick question to Tianqi Liu. And my question is, what would you say is the most surprising finding that you've had from your study of the Alaskan lithospheric structure?
I won't say there's anything really surprising at this point, because there are a lot of already traditional seismic inversions for Alaska using the Earth scope data right now. But our hope is really to enhance the resolution, especially the resolution to better localize these features. That's really our aim. So I won't say there's much really surprising. I guess anything that we see right now has something in the previous models as well. So.
Okay, thanks a lot.
Yeah.
All right, so according to my computer, we're at 11:34, so I think we can come to the next two talks in our session. So our next speaker is Ian Lum from York University, and the title of his presentation is Heuristic Measures as a Prospect for Data-Driven Discovery, Application to Observations of Relative Paleointensity During Transitions of the Geomagnetic Field. The floor is all yours.
Thank you, Fiona. Title's a bit of a mouthful. What I want to do is to talk about this notion of being able to actually derive governing equations, in some cases partial differential equations, from observations. And in terms of the geophysical applications, we're very motivated by ongoing efforts of Professor Aldridge and his colleagues in the area of looking at measurements such as paleointensity data and so on. What we're finding is, as we seek to apply some of these technologies that are in an unbelievably rapid phase of development, we're encountering some interesting challenges. So in terms of giving you a little bit of background, I'll give a sense as to what this idea of data-driven discovery is, talk about how, in order to get to places that will allow us to work with heuristic data of interest, such as paleointensity measurements, we need to account for them and try and provide some summary work along the way. So here's a recent, I think it's a May 2022 article that appeared in Quanta magazine, where there is reference to this notion of trying to extract, distill. You'll hear various phrasings of this notion, trying to somehow extract equations from data. And the promise, as you can see here, is quite substantial. The idea of hearkening in a new era of so-called GoPro physics, the idea that perhaps you could have a device on your smartphone, such as a Google Lens, and you could cast that onto experimental results. I'm showing here a snapshot of some experiments that we did previously, where we're looking at instabilities in rotating contained fluids, and remarkably deduce the equations that relate to that. If you are a little bit skeptical about the possibilities of this, you're to be encouraged. I think that's completely reasonable. In terms of more of a practical example of how this actually happens, the idea is that you would sample data in various ways, compute spectra of that data that would allow you to then compute various kinds of derivatives. The problem can then be formulated in terms of a set of linear equations. And the features here are basically the different components that you might find in your partial differential equations, such as a second order spatial derivative, time derivatives of various fields, and so on. And then the idea is to find the unknown, in this case, the alpha vector here, which gives you the strength of the various coefficients. So this is the basic idea. Now, this recent work, this sort of recent reinvigoration of this whole prospect dates back not so much to this paper, but to a previous one that it was published in about 2016. So it is a very recent field. And some of those early methods have now led to more, let me call them state-of-the-art methods. The way that they're in the sort of machine and deep learning research that researchers proceed is they take a series of governing equations. So in our case, we'd be interested in, for example, doing some kind of modeling or simulation of the geodynamo. Obviously, that's pretty involved because we're looking at the magnetohydrodynamics of a rotating fluid. So quite involved pursuit. From that, we would then be able to extract various measures of fluid flow and other interesting parameters. If we're talking about the magnetic field, of course, various parameters describing the field and its behavior and so on. Then the idea is that what these this is used essentially as training data from the machine learning perspective. So this data that's produced through forward modeling is sampled, passed through essentially a deep learning network, and then the so-called coefficients of the governing equations are deduced. The method benefits from a matrix representation that is rather sparse. So essentially the key technique that's being exploited here is something called sparse regression. The method has been shown to be quite effective with partial differential equations, such as looking at the turbulent flow of a fluid past a cylindrical object, for example. The method that I'm talking about here, this deep pi mod, has advanced beyond some of the earlier efforts, which were really compromised by being particularly sensitive to noise and requiring very, very large volumes of data. So a lot of advances have been made there. Differentiation is part of the method. Anybody who's worked with numerical methods knows that that can be concerning. There are techniques that are being applied known as automatic differentiation that are providing more stable results. But none of that really gets us to being able to work with what I've called heuristic data. So if you took something like the results of simulating the geodynamo and you looked at the intensity of the dipole component of the field, the main axial dipole component, you'd have a data set that would ultimately look something like this. And of course, we have observations of this as well from a variety of different sources. And we're really motivated to look more closely at this data because it's coming from different sources, including traditional paleo intensity measures, but also from beryllium isotope data. I talked about this a fair bit last year at the CGU. These data sets are getting to be quite high resolution. They capture the magnetic field during reversals and excursions of the field. And they're a bit odd in that they exhibit this asymmetry. So it seems that during this critically interesting period of the transition of the field, we have a window into observing the field in transition, and the fact that these asymmetries seem to be a fairly robust feature of the various data sets encourages us to want to look at that data in more detail, particularly and ultimately, I suppose, to try and tease out what might be the relative contributions behind the geodynamo, the mechanisms involved. That, of course, being a very interesting topic to those of us in this area in and of itself. I should say that Keith Aldridge and myself and others have had a long-term interest in looking at, let me call it non-traditional means for driving the geodynamo, means that don't rely completely on pure thermal convection or compositional convection, the introduction of other possibilities. Now, if I bring back the schematic that I showed you before, what we were talking about is a method that can handle basically flow fields, potentially other kinds of fields that are the product of a forward model. But these heuristics, such as paleointensity data, would be what I've called here a derived output, something that is could be derived from the forward modeling study, but is not capturing the fully embraced, spatiotemporal time sort of fluid flow. So that's not really the existing sweet spot of methods such as deep PyMod or others. So what we're very interested in doing is working with these heuristics. And as I say, paleointensity data is our primary area of interest right now. So what I've added to the previous slide is some kind of an input here, which has kind of been left unspecified, but we're assuming that we have various observations of paleointensity data, which indeed we do, from a variety of different places, global, more or less globally distributed. And I would even throw in here the observations that are more recent from these beryllium isotope records and so on. So we have various kinds of heuristic measures here. And the approach that we're currently having a look at, so this is very much a work in progress kind of update that I'm sharing, is to work with some kind of a forward modeling scheme to try and produce flow fields, extract from the flow fields heuristics, and then engage in some kind of a correlation involving the heuristics to see how well the observations align with what we're getting from the forward modeling study. And then to try and close that gap using a feedback loop to at least get some kind of similarity, if you like, by working with this correlation. Once we have that similarity, we can then run through the same sort of discovery process and estimate the coefficients of the governing equations. Now, of course, you may be saying to yourself, well, why would you do that when you've already made adjustments on the forward side? We believe there will be value in doing this and expect that any discrepancies that are found would be potentially would be of interest. Just in terms of some feedback that as we start to look at this approach ourselves, we're trying to extend the area of that is existing as far as doing this data-driven discovery. As I say, it's a very rapidly evolving area, and because a lot of the folks that are building the methodologies, the approaches, and so on are not physical scientists or other kinds of scientists. Their emphasis is elsewhere. And so a lot of what we're doing is, I think, motivated by having to work with the challenges that are inherent in working with real observations. And I do think that geophysical observations are particularly interesting in this regard. One of the challenges that you have that's inherent in deep learning is that you're constrained by what you train on. So this is why we feel that there's a need to put in this feedback loop to try and make some attempt to improve the alignment between the training data and the data that we seek to discover, so that we can enhance our prospects there. As I mentioned, we are focused on correlation here, at least initially, and so there are elements of non-uniqueness that are inherent here. However, there are interesting prospects that are also emergent in the machine and deep learning research areas that might allow us to introduce elements of causality later on, and also look at the parameter space in a much more strategic way. So as I was saying, this is an exciting and interesting field. The breadth and depth of possibilities are quite stunning here. We are very interested in applying the approach to trying to further our understanding of the geodynamo. This should be regarded as something that is complementary to the approaches that are taken today, which are fairly broad and deep. We're motivated by trying to bring into the fray our long-standing interest in paleointensity data for a number of different reasons. And curiously, the analogies as I work through this, the analogies to things I've run across in seismology continue to amaze me. So I think with that, I'll go ahead and close off and see if there are any questions to answer.
Okay, thank you very much. And we have 1 minute for questions. One's just come in from Julian Lohman. Very interesting talk, Ian. Are you able to comment any further on uniqueness issues? I heard you mention that problem at the end. I was typing.
Yeah. I mean, you know, we are, unless we come up, and again, if people have suggestions or if you've run across, we've already had some great feedback for some of the other talks. You know, if you can think of other ways of perhaps hedging our bets here. I don't know that there's any way around this, Julian, because ultimately we seem to be limited by, you know, whatever we do here in terms of looking for coherence between these derived data fields. And so, I mean, we'll be able to look at, we'll be able to do things like look at, you know, spectral similarities and so on. We could look at all kinds of different measures, but I think that's, at least as far as our thinking currently, the limitations are inherent, and you know, that'll be definitely something we'll want to drill into. So not a great answer, but at least an honest one.
Great, thank you very much. And that brings us to time. So
thank
we'll
you.
Swap over the presentations. And our final presentation, this is our third student presentation of the session. It's by Mark Lipitzke from the University of Saskatchewan. Application of a geophysical technique to supplement geotechnical analysis of slope stability problems. So if you'd like to share your screen.
Yep, you can hear me fine now.
Yes, loud and clear.
Hopefully see a screen now with nothing on it yet. Okay, yeah, my name is Mark Lipitzke, and I'll be presenting on the use of geophysical methods to help characterize slope stability. So I've only got about 12 minutes. So if it's unclear exactly why we care about slope stability, I'm going to have to direct you to any of these homeowners along the riverbank on Saskatchewan Crescent in Saskatoon, Saskatchewan, Canada. This isn't a localized problem either. Each one of these markers indicates a failure in Saskatoon within the last 100 years. And Saskatoon is only one city of many that lies along the Saskatchewan River system. So in order to properly characterize the slope stability problem for geotechnical analysis, we need a few bits of information. We need to define the geometry of the problem. We need to estimate the physical material properties. And for proper site characterization, we need to calculate the in situ stresses. The scope of my research is limited to defining the geometry and estimating the material properties. So where do we start? Well, the first and obvious step is to drill. There's a reason why they're often referred to as truth sticks. Drilling returns highly reliable information about the lithology, and the samples can be analyzed in the lab to extract very precise measurements of the material properties. This sounds perfect, but there are cons. The first and obvious one is the cost. Drilling is expensive, and secondly, it's invasive and frankly ugly. No one wants to run into a drill on their afternoon river walks. Thirdly, while the results are reliable, they offer only samples of the subsurface at discrete locations throughout, leaving the rest into blind interpolation. So, are there any alternatives? Yeah, so let's try this again. This time we'll start off with more drilling. It would be naive to think that we could entirely replace drilling with the magic of geophysics, but hear me out. Instead of drilling all of the holes from the previous example, we supplement 1 or 2 holes with a collection of high-resolution geophysical data. For the sake of this example, let's say we collect electrical resistivity. In reality, there are many different types of surveys, and it depends on the material properties important to the project at hand. So after data collection, a continuous geophysical model may be created through the area of interest. Now, instead of blind interpolation, or worse, even just guessing of how the subsurface behaves between the boreholes, we can use a geophysical model to interpolate through the area, giving us a more realistic solution to the geometry problem. So now that we've got the basics nailed down, let's talk about real-world applications. The 2 images here show the riverbank along Saskatchewan Crescent and 16th Street in Saskatoon between 2013 on the left and 2021 on the right. The main failures here occurred between 2014 through 2016, and movement was documented as late as 2019. Our aim is to apply geophysical methods here in order to help characterize a site for use in future assessments. The geology of the riverbank has been thoroughly documented over the years by many previous investigations. The stratigraphy shown on the left is local to our area of interest, but for simplicity, we can reduce this down to only a few features. We have clay, which is electrically conductive. We have not clay, which is not electrically conductive, and we have the contact between the two. This contact is a failure plane for most failures documented within city limits, and it's the main aspect of the geometry of this problem. Shown here are a handful of commonly used geophysical methods. Of these, those circled in red are generally more useful in defining the geometry of the problem, and those circled in blue are more useful for estimating material properties. While many of these add value to the overall solution, the heavy hitters here are LiDAR, DC resistivity, and the multi-channel analysis of surface waves. So these images here are snapshots of data collection through the process. The left image shows the elevation model collected with LiDAR data. The middle image shows the locations used in the high resolution DC resistivity survey, 3D resistivity survey. And the image on the right shows a spread of geophones used in the seismic collection. So for the 3D DC resistivity, over about a week, we collected over 500,000 resistivity data points, which is shown in the point cloud on the left. These points were then QC'd and fed into a SIMPEG resistivity inversion, 3D inversion. And the model on the right is a isosurface of the resistive features spit out from the inversion process. So this image here shows a slice of the 3D resistivity model where the blue is conductive and red is resistive. The white line indicates the contact marked by the. However, we can see that the resistivity model shows a contact that undulates through this area. So this comes back to where the drill log will place the contact at a very discrete point, and at that point it's correct, but everywhere else it might undulate a bit, it might move. So it's important to get a continuous image of that contact. LiDAR and DC resistivity are used to satisfy the geometry requirement to this problem. So now that we found the contact in differentiated layers, the next step is to estimate material properties. To do this, we primarily use the seismic method multi-channel analysis of surface waves. From here on out, I'll refer to as MASW. In basic terms, first we set out a spread of geophones and whack the ground with a hammer, which then generates surface waves of many frequencies that travel through the subsurface and are recorded through the spread. Lower frequencies, such as the green and the red here, have larger wavelengths and are more sensitive to greater depths, but this is at the cost of spatial resolution. The purple and the blue waves are sensitive to lesser depths, but have a higher spatial resolution. So here is the data collected from a single MASW shot. The raw recording for a single source is shown on the right, where each trace represents a single geophone. The image on the left shows the wave dispersion curve of the recording, which indicates the estimated phase velocity distribution of waves at each sampled frequency as they pass through the spread. This specific image actually shows the slowness or the interval transit time, the inverse of velocity, but it's the same concept. The goal of MASW is to estimate the shear wave velocity for waves through a range of recorded frequencies, and the lower the frequency, the deeper the sensitivity. So the product of an MASW survey is a log of information relating the shear wave velocity to depth in the subsurface. Through analysis and inversion of many combined records, a 2D section of the shear wave velocity variation with depth can be created, as shown here. I didn't have final results for my data collection, so this is an example. So why are these values important? There are many different properties important to the stability analysis. But due to time constraints, I'm going to only show 2 to represent the process. From seismic velocities, we can make estimations of material properties such as Young's modulus and Poisson's ratio. I must insert a disclaimer here that these are just estimates. It's extremely important to use sources such as drilling or trenching in order to anchor these values to real-world values. So let's talk about Young's modulus. Young's modulus is important as it is a measurement of how much the material resists deformation in the same axis of an applied stress. This is an important property of material strength. Poisson's ratio describes how the material experiences deformation in an axis perpendicular to the applied stress. If you think of squeezing a marshmallow and having the sides bulge out. So why are these values important? Let's consider a very basic example where we have a layer of clay. We provide a downwards force, let's say gravity, which then creates a vertical deformation and then leads to a horizontal deformation. This horizontal deformation pushes between the particles of the clay, which then creates a horizontal stress. So now imagine we have even more clay underlain by a more rigid body, such as like a sandstone or shale, glacial till, and a retaining wall at one end. We now have substantially more downwards force, and due to Poisson's ratio, we have an increased horizontal stress as well. As this force builds, the mismatch of horizontal forces between the materials grows until the contact shears, and the 2 layers become uncoupled, causing a displacement of material until equilibrium is reached. So in order to properly characterize the slope stability problem, we need a few bits of information. We need to define the geometry of the problem, and we need to define the information regarding, or we need to estimate the physical strength properties of the material. So in order to define the problem geometry, the basics are the topography and the slip surface, or the stratigraphy. We collect topography data using LiDAR, and in this specific scenario, we were able to accurately image the contact using DC resistivity. And in order to estimate the physical material properties, we've used MASW and refraction seismic, which I haven't talked about here. There are a few different methods that I've glossed over, but I want to get the heavy lifters in here. So with that, I'd like to give a special thanks to the University of Saskatchewan for providing the research opportunity, Axiom Group for collecting the LiDAR data, and to DS Geophysical for supplying the equipment and personnel for the 3D resistivity collection. That's it.
Great, thank you very much. So are there questions for Mark? We've got a couple of minutes before the end of the session. See if anything comes into the chat in the next couple of moments. maybe I'll jump in with a quick question in the meantime. You mentioned that the geology of the riverbank is characterized by clays over the top of tills, so very conductive over less conductive. Does that ever cause a issue for your DC resistivity monitoring, or does the presence of a conductive layer at the top not cause too much of an issue in terms of penetration to the depth that you want?
So that's, yeah, the very valid question. So in this scenario, the upper clays are between 2 to 3, well, they actually pinch out within the area, but at max they're maybe 8 meters deep. So it's not, in this scenario, it did not provide any issues. We were able to clearly see through it.
Okay, thanks a lot. And there's a question in the chat from Pascal Audet. Says, thanks, Mark. How will these improved estimates of bulk modulus and Poisson ratio be used to help in monitoring?
Well, so the goal is to be able to acquire values for these sort of parameters that are continuous throughout the project area. So that can be useful in more accurate geotechnical modeling. And it can be used, well, hopefully in, say, like a 4D survey application where you apply the same survey multiple times over a time frame. You can estimate how maybe these materials or the properties are changing over time.
Great, thank you very much. Quickly typing a reply into the chat. There we go. Okay, are there any more questions either from Mark or any of the other speakers? All right, in that case, we've actually come to the end of our official session. So just a couple of quick reminders before we wrap up. First of all, as you saw, we've got 3 posters, so you can go into the poster gallery section of the conference website to view those posters in detail. And I believe there are ways and means to contact the poster authors if you have any questions or comments on their work. The other piece of housekeeping that I'd like to remind you of is for Solid Earth section members. You should have received an email from Andrew Schaefer last week with a Zoom link for our Solid Earth section AGM, which will be tomorrow, either late morning or early afternoon, depending on what time zone you live in. So please join us at the Solid Earth section AGM tomorrow. And that's it. And I'd like to thank all of the speakers and all of the participants, and especially our colleagues from Georgia who joined us in their evening. And with that, I'd like to stop the recording and thank everyone very much once more.